Hey guys, last week I gave you an intro to functions, basically what they are and how to create basic ones. This week we're going to continue that, going over some more interesting concepts that are involved with functions. A curried function is a function that is applied to its arguments in a particular way. Consider the following function that takes two arguments here, add. Add, looking at its type signature, is the same as a function that takes an int and returns another function that takes an int and then finally returns an int. So what are the consequences of this? So basically, we can apply arguments to add one at a time here. So we could say add 5 creates another function that takes an int and another int. Notice when assigning this function add 5 here, we don't even need to specify its argument y. So there's implicitly an argument y here when you return add applied to just one argument. So this is a function here, but you notice there's no argument specified here. That's okay. The argument is implicitly there. Add 5 returns a function. Pretty cool, eh? In Haskell, all of our functions are curried by default. Now, this is not the common for most programming languages, but Haskell is an ultra cool, ultra sophisticated programming language. Currying is particularly useful for working with something called higher order functions. Now, a bit of a warning here, we won't be talking about higher order functions for a while, so I'm just bringing this up as a bit of foreshadowing of what's to come. It is possible to specify a uncurried function, basically just by using a tuple. So instead of writing your arguments one by one like you usually would, you group your arguments into a tuple. What does this mean? This means that you can only call the function by specifying all of the arguments inside of the tuple. So now it's not possible, you restricted it so that it's not possible to specify the function one argument at a time. You have to specify them all at once. So an example of this with the add function from before is we take those two, instead of separating them by the arrow operator, we take the two inputs and we group them into a tuple. And the implementation is going to look like a tuple as well when we write the arguments. Polymorphism is a very useful feature of a programming language that allows you to create functions that are generalized over a variety of types. So take the length function for instance. The length function takes a list and gives back the number of elements contained in that list in the form of an int. It'd be very, very annoying if we had to create different length functions for different types of lists. So say we had a list of integers and a list of bool. It'd be very, very annoying if we had to create different length functions for each of these list types. Instead, the default length function, we're able to write the type signature for it as length takes a list of A. So note, A is not a type here. We can tell it's not a type because it doesn't begin with a capital letter. All types have to begin with a capital letter. Whenever you see something that doesn't begin with a capital letter in place of a type, that means it's basically a placeholder. So just like in algebra where we use like x and stuff as a placeholder for actual values, this is a placeholder for a type. You call it a type parameter. A good intro example of a polymorphic function is the fist function, which takes a tuple and returns the first element of that tuple. So you can see the generalized type that VS Code is trying to give me, the most general type, is just A, B goes to A. Okay? So the nice thing about this is I shouldn't have to write a different fist function that for working on different types. So I shouldn't have to write a different function that's going to return 1, okay, when working on a tuple of 1 and 2, or a function that's going to return true when working on a tuple of true and false, okay? I shouldn't have to define different, like, fist int and fist bool here. Because if you were to look, like, how would I define fist int? If I had a function fist int that worked like int goes to n, how would I define this function? Well, I would define it as x, y equals x. Same thing here, right? Same as, how would I define the function this bool, 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 goes to bool. Same way, right? So the idea here is I could define these functions that restrict what type I'm doing, or I could just notice the fact, well, that all of these have the same implementation, right? And it is of x and y equals x, okay? All of these functions are going to be written the same way, regardless of what type it is here. So if I leave the type signature using type parameters a and b instead of specifying the specific type, now I can use this one fist function for all of those different types. Some other examples of polymorphic functions include these list functions like reverse and head and map. So reverse, for instance, takes a list of A and it returns that same list of A, but in reverse. It reverses all of the elements. So notice how this is a list of A goes to a list of A, not a list of A goes to a list of B. That would actually be the wrong type. Why is that? So whatever the input type A, so you're going to have an input, is going to be list of A. And whatever that A is, it could be anything, but then the return type has to be that same type A. Okay, so you're specifying whatever the type of the input is, the output has to be that same type. This is the same as for head. You're saying head takes a list of A and it returns the first element of the list, okay? So whatever the input type is, it's some list of A. The output type is going to be that same A. Now map is a bit more of an interesting function. So map, it takes a function as its first argument, okay? So its first argument is actually a function. And then what it does is it takes a list of A as its second argument, and it goes through that list, and it applies the function to each element in that list. So the function takes an A as input. So it's going to go through this list, and it's going to take each A, and it's going to turn each A into a B. So then the output is going to be a list of B. So make note when writing polymorphic functions, whenever you specify a type parameter, the output type might have to be that same parameter. So you can't just say, well, it takes a list of A and returns any sort of list B, when in fact the output type depends on the input type. A good example of this would actually be applying the map function to fist. Okay, so let's say we use map and we use map with fist of a list of tuple of 1 true, 2 false, 3 true. And we get back a list of 1, 2, 3 like this. Okay, so let's look at the type. So the type of the map function is a list of A, or sorry, it's a function that takes an A to a B and a list of A and then returns a list of B. So let's paste this up here just to keep track of it. And then the type of the fist function is a list of A or a tuple of A and B goes to A here. Let's paste this here. So the first thing to note is that when I'm defining the type signature for map, okay, this has nothing to do with the type signature for fist. So I can actually replace this. Instead of writing A and B here, I can just write basically anything else. So let's say M and N, as long as it's lowercase, goes to M here, okay? Now the interesting thing that's going on here is when I apply the map function, so when I do this operation above of applying map to fist, and it applies fist to each element inside of this list, okay, the function A goes to B here, that's the same as this right here. So the A goes to B, okay, is actually, in this case, MN goes to m. So the trick here to notice is that a equals mn and b equals m. And actually, sorry, b, no, sorry, b will equal m. Just a note, as none of this stuff is meant to be loaded into GHCI, in case some of you guys were trying to load into GHCI. I'm just writing it to explain it to you. In fact, you might have noticed beforehand, when writing FIST and stuff, these are functions that are already defined. So if you try and define them again and load them into GHCI, that'll give an error. Okay, so in this case, the A goes to B is actually this FIST function. The moment I give map this FIST function, it's doing this like substitution where A is actually mn, the tuple of mn, and B is actually m here. So then this list of A here ends up being, guess it, what's A here? The list of mn. And this list of B ends up being, you guessed it, okay, this list of B here, what's B? A list of M. So we have to play this game. It's just like algebra, the algebra you learned. You have to play this game where you're substituting in the types as necessary. If you have a function g that outputs the same type as the input of a function f, you can compose them into a new function z, like so. So the trick is to use this dot operator. So the trick is f will have the same input type as the output type of g. A good example of this is if we wanted to define a function lastElem that will take a list and will return the last element of that list. So this is kind of the opposite of the function head I showed you before that takes a list and returns the first element of that list. So we create this by combining that head function actually with the reverse function that I showed you before. So let's say I have head composed of reverse. Okay, so just as a reminder, reverse here, it takes a list of A and returns an A, okay? And reverse takes a list of A and returns a list of A. So reverse takes a list of A, returns a list of A, and then head takes that list of A that reverse returned and returns an A. So these both chain together to create a function that takes a list of A and returns an A. And just like before where I showed you with the curried functions, you'll notice that this is the function, but I'm not writing its argument. So there's no x's here. Okay, I don't need to write its argument. Rather, I would say that its argument is implicitly there. If I were to write its argument, what I would do is I would write x's here, and then I would put these two things in brackets and write x's afterwards. So I put these two things in brackets just to be like, these two things get put together to create one function that then gets applied to x's. Now that we learned the composition operator, now is a good time to bring up another extremely useful operator that is basically this $sign operator. So this $sign operator is very useful for dealing with parentheses. So in functional programming in particular, we get a lot of buildup of parentheses. So here I have a kind of complicated expression. You're not going to know exactly what's going on in it right now, but I've just written it down to illustrate how easy it is to build up this like backlog of parentheses. And you can imagine when writing this expression, when fixing all of the parentheses at the end here, you might miss one or add an extra one, and that screws up your program. So to make this a bit easier, we can use this $sign operator. So we have this mashed up function here with all of these parentheses. So what we could do is we could get rid of some of these parentheses. So wherever we have a parenthesis that runs all the way to the end of the expression here, what we do is get rid of this one and instead put a $sign here. So this $sign, it assumes to be this a parenthesis and it ends all the way at the end of the expression. Okay, so we can put a $sign here. Now we might be tempted to put a $sign here, but we can't. If we were to put a $sign here, it would screw stuff up. So like, let's say I deleted these two. This wouldn't be the same thing as what I had here where there's two parentheses over here. This means a $sign, parenthesis, open parenthesis, and parenthesis at the end here. So we can't put a $sign there. But this parenthesis, see this parenthesis goes right to the end. Another $sign. This parenthesis goes right to the end here. Another $sign. Finally, this parenthesis right to the end here. Another $sign. And see how much nicer this is? It gets rid of all of those piled up parentheses at the end. It can't get rid of all parentheses, so like the parentheses I needed for the plus sign and the +2 here I need to keep, but it still manages to get rid of probably the most annoying parentheses, which are the ones that pile up at the end there. Type classes are a very important feature of Haskell that extend your ability to do polymorphism. They allow you to find functions that have different implementations, so that means the actual definition of the function, like the thing besides their type signature, is going to be different depending on the type of their input. So these functions that belong to a type class are called methods, is another name for them. So a good example of this is the Prelude type class. So this is a type class that already exists in the Prelude, and it contains the following method. Okay, this is EQ. The double equals and the slash equals, which means does not equal. So this allows you to compare values. So in order to actually use this type class, you need to make an instance of the type class. So you notice the type class definition, it only has type signatures. So there's only type signatures here. And there's a type parameter to it, A. Now, when we make an instance of the type class, what we're going to do is we're going to say the instance, we give it the type for A, in this type instance, bool, and we say this is how double equals is going to be defined for bool. So we're saying x double equals y, and we check if x, which x is a Boolean value, so this is the same as saying if x is equal to true, then if y is also equal to true, then we return true. Otherwise we return false. Else, if y is also equal to false, so if both of these things are false, then we return true, otherwise we return false. And does not equals, we can define more simply because we already defined equals as just being the not of the double equals. The cool thing here is that we can make more instances for int and float and so on. However, those are a bit more tricky to find for equals here because int and float and all of those things have infinite values. But each type here, okay, is going to have a different definition. Now, there are a variety of pre-built classes that come inside of the Prelude. So for equals is one of them, and it's defined for all of the basic types. So all of the usual types that we use, like bool and char, string, int, integer, float, all of these things, EQ is already defined for. So you don't have to make definitions for it. That means you can use this double equals operator and this does not equals operator with any of these types. And there's some other types like show, read, which we don't really need to worry about for now. And then there's even more complicated types that actually depend on the other type classes. So when I'm saying EQ and I use this operator here, this bind operator, ord, what I'm saying is in order to have an instance for the orderable class for any of these types, you already have to have an instance of the EQ type. So in order to have an instance of bool for the orderable type, which allows you to basically say, is this less than this, or is this greater than this, you already have to have an instance for EQ, which would kind of make sense, because does it make sense to be able to say, oh, this thing is less than this other thing and this thing is greater than this other thing, when you can't even say if these two things are equal to each other? So there's a few more classes like this. One that we'll see a lot is the num class. So the num class is what defines the operators like plus and minus and times, the basic arithmetic operators. And then there's some more complicated classes that depend on the num class, like fractional class. So if you use division at any point, you'll see that it needs to be part of the fractional class. And there's two types of division. There's integer division, which is that div thing, and then there's the division, which is the slash, okay? And that's the floating point division. We'll talk a bit more about these later. A polymorphic function is called overloaded if its type contains one or more class constraints, which basically is a result of a function using a method from a type class. So take the function sum, for example. So sum takes a list of A, it sums all of the elements inside of that list, and returns the result, which will be another type A. Now, we could have written sum as being the list of int goes to int, or the list of float goes to float. However, the most general form of its type has to do with the fact that it uses the plus operator. So the plus operator is part of the num class. So what we do is we write it polymorphically, saying this could be any A, except it has to be an A that is part of the num class, that has an instance of the num class. So take this function add, for example. So we could write a function add that adds together its two arguments, x and y. And we could give it the type signature int goes to int goes to int, and that's fine. However, now it's constrained to just working off of int. So if we want it to work with float or some other num type, we would have to then define another add function. So what we're better off doing is giving it the more general type, its most general type of num A, and then we use this bind operator thing, which is the equals arrow, and then we just use the type parameter A. So we're saying this function, instead of just being an int goes to int goes to int, it can be any A as long as that A, that type A, has an instance in the num class. Okay? So in general, when we write a function that uses a method of a type class, we're going to have to specify in its type the type constraint like this. Another example along similar lines as the add function is if we wrote a divide function that uses the fractional division. Okay, so this operator, this division operator, is part of the fractional class. So its most general type. So we could write, for instance, divide takes a float and another float and returns a float. Okay, but that wouldn't be its most general type. Its most general type would be an A and another A returns another A, where that A is any A that has an instance of the fractional class. Now, a good trick for investigating this stuff is to load up GHCI, and you can actually use this special, it's like the type method, okay? You press a colon and you write info, and you ask for info. You could actually info anything, but a good use is info the operator. So if it's an operator like this that's meant to be used in infix notation, so in between two things, put it in brackets, and it'll tell you that, oh, this operator is part of the fractional class. And then we can ask it for info like, all right, let's ask what's the fractional class all about? So just colon info. So in general, you can just colon info almost anything you want to learn more about. And if you write colon info, you'll see it defines the fractional class. It tells you what are the methods inside the fractional class. So there's actually a few more methods. This recip and from rational. Let's just ignore these for now. And then it also tells you what the instance is of the fractional class. So the fractional class works on float and double. So if I have this divide function, I can say divide 5.0 and 2.5, right? And I could force it to be a float, or I could force it to be a double by explicitly writing the type with this : afterwards. Okay, and this will be more important if you're actually doing a irrational division. The double and float, you'll see double allows you to have more accuracy than float here, but float will be faster. Okay, so you might want to switch between the two. So if we write divide with the fractional class here, it's going to be more flexible. And there's also another divide that we could have created called divide 2 that uses a different division, x div. We use the backticks here because div isn't like an operator like this. It's just a normal function. So if we want to use it in between notation, like infix notation, we have to use these backticks. So remember that backtick, that's at like the top left of your keyboard usually. X div y, and you'll notice the div function does integral division. Okay, so integral division means that it's going to be an int type of some sort. So if we have, we could save this, make sure to save before you reload, and you do :re to reload here. You divide 2, 2, 3. What ends up happening? Well, this just returns 0 because it's literally going to say how many times can 3 go into 2 as a whole number like this, right? So because it's an integral. And there's usually two, if you ask for info on the integral class, there's a few different definitions. Let's ignore word for now. The most important ones are int and integer. And int and integer are similar to float and double in that int is smaller. It's only able to track numbers so high, and then integer is able to basically be as large as you want it to be. In my other tutorial this week, I go over conditionals and I go over pattern matching. Pattern matching is very useful for a variety of data structures, in particular lists. Lists are a very important data structure. I'll go over what I mean by data structure in particular next week, but for now, just take it for granted. Lists are a very, very important data structure in Haskell. That's why I brought them up right away. And usually the way I've been showing you to write them is using this special syntax with square brackets and commas. Now, the interesting thing about lists is that this syntax of square brackets and commas is just kind of a special illusion that you're allowed to use. We would call it syntactic sugar. A lot of programmers would call it for this right here. So the way you could think of a list is a bunch of elements. So each of these things are individual elements of the list that are put together using this operator, this : operator, which you can call the cons operator. And you put it together using the cons operator until you get to the end of the list, and then you specify this special value, which is, you call this the empty list, and it's just 2 square brackets with nothing in it. So every time you see a list written like this, you can also interpret it as being, this is how it's actually written under the hood. Okay, so this is what's actually going on here. Now, the interesting thing here is we can define functions that use patterns, okay, of x : x's. So in this instance, x here would be, let's say, 1, and x's would be the rest of this list, everything else in the square brackets here. So let's say I wanted to write the function head, which pulls the first element of the list out. So all I would do is I would pattern match x colon x's, and I would just give back x. Conversely, if I wanted to write the function tail that removes the first element of the list, I would pattern match x colon x's and just give back x's. Okay, so keep this in mind. When I write the pattern x colon x's, x is the first thing, x's is the list that's the rest of the list. Now, you need to note x colon x's doesn't pattern match to empty list. So generally, whenever we write a function that pattern matches, so you should basically never ever write functions like this that just pattern match on x colon x's. What you should do is whenever you're pattern matching on a list, you should always pattern match on at least x colon x's and the empty list. So these are the two scenarios. Okay, so if we look back at our tail function from before, the proper way to define tail, okay, so that it won't crash if you give it an empty list, is to give it the empty list case and return the empty list here. Now with head, this is a bit trickier, because what do we want to do? So with head, we say, okay, in the case that there is a list, okay, with at least one element. So there's at least one element to this list here. This x colon x's. If it pattern matches here, then let's say it's the element of, let's say it's the list of just one value. Then x will be that one value, and x's will be the empty list. Okay? So as long as there's one value, it'll return it. If you call safehead on the empty list, we need to return something. But what do we return? Well, with safetail, we could return the empty list again, because safetail returns a list of A. It takes a list of A and it returns a list of A. But with safehead, it takes a list of A and it returns an A. So we can't return this. And because head is polymorphic, because it's just some type A, we can't just return some random value like 0 or something. So, long story short, there isn't a good way to handle this right now. You kind of just have to let it crash. So what you would do for now is you would just use the error function from before. There is a better way to handle this in the long run that I'll show you later, but it's going to have to be many, many tutorials later. Lambda expressions are going to be very, very useful in a bit, although at the moment you might not see a use for them, but just take my word for it. So lambda expressions are a way of writing anonymous functions. So these are functions without a name. So you use them instead of putting a name. So instead of writing, say, f of x here equals x plus x, you just write /x, and then you use this arrow, and then you write the function definition. So we could define any function that we've written before where we explicitly put the parameters on the left-hand side. We could define them with lambda expressions and put the parameters on the right-hand side. And we would do this in curried form like this, where we're saying we have a function that takes an x, and this returns another function that takes a y, that then adds x and y together. So like I said, this allows you to define a function without actually having to give it a name and just kind of putting that function like right in its spot, wherever it needs to be. So I already gave you a little bit of an introduction just a bit earlier to the map function, which is a very useful function that takes a function as its argument, which is a very interesting thing that we'll talk about a lot more later. And it takes this function as its argument and then a list, and it applies the function to each element of the list, returning another list. So take, for example, if we had a function add1 that just adds 1 to its argument, and we wanted to go through a list and we wanted to add 1 to each thing in that list, we could map this function add1 to a list x's. Okay, so if we created this function sum1 and we gave it 1, 2, 3, it would return back the list 2, 3, 4. Map is very useful. So I'll show you one example right now of lambda expressions. So lambda expressions are very useful with map because a lot of the times you don't want to define, say, this add1 function right here. You don't want to have it just hanging around there somewhere inside your file when the only place you need to use it is inside of map right here. So you could just define a little lambda expression. Before we conclude this tutorial today, I'm going to give you a bit of an intro to the concept we're going to be going over next tutorial session, which is a super important concept known as recursion. This is a very important concept inside all of computer science. So recursion gives you the ability to define functions by using the definition of a function or using a function inside of its own definition. So take map, for instance, the way we would define map. So we would define map by first applying so f is a function that takes as input, and we would apply f to the first element of the list. Okay, so we would pattern match on the list, x's, and we apply element f to that first element. And then what we're going to do is we need to return another list. So we're going to rebuild the list. So we're going to use this colon operator. So this is an element, and we're going to use this colon operator to then create more of a list. So then we're going to call the function map inside of its own definition. So we're going to use map inside of its own definition. We're going to give it f again, and then instead of giving it the whole list back, its argument, we're just going to give it the tail of the list x's here. And we're going to keep doing that, and it's going to keep evaluating this part right here until x's becomes the empty list, and then we just return the empty list here. So to really understand what's going on here, let's look at an example evaluation. So let's say we have our map function here, and we try to apply a function +1 to the list of 1, 2, 3. So remember, the list of 1, 2, 3 can be seen this way. This is the true form of the list, where it's put together using these colons here. So it pattern matches this list here. There's two scenarios. It's either going to pattern match to this or this. So it's going to pattern match, because there's colons still, it's going to pattern match to this. Okay, so 1 is going to be x here, and 2, 3 empty list is going to be x's. So what it's going to do is it's going to take 1 plus and add that to x. So we're going to have 1 plus 1 colon map 1 plus, and then x is here, remember, is 2, 3 empty list. So we're going to have 2, 3 empty lists here. And then what happens is, now ignore the rest of this part here, and let's just focus on evaluating this again. Okay, so now we have map 1 plus and 2, 3 empty list here is pattern matching to either x's or empty list. So there's still a colon here, so it's going to pattern match to this. And now this time, x is going to be 2, and x's is going to be 3 colon empty list. So then this time we end up with 1 plus 2 map 1 plus 3 empty list. Okay, so this gets evaluated again. And see, this just keeps happening until we get to map 1 plus an empty list. And then this time it pattern matches to this case here, right? And then what does this get turned into? Empty list. And now you can kind of like go back and you see now it'll evaluate all of these additions here. And you have the list of 2 colon 3 colon 4 colon empty list, which you know is the true form of this list, 2, 3, 4. And with that, we finally conclude our tutorial today. I know this was a very big tutorial, because we're at the beginning of learning Haskell. You have to kind of learn a bunch to get out of the way to get to the more, believe it or not, complicated concepts inside Haskell. So I know this is a lot. However, the tutorials will shorten up in length in the future. They'll shorten up in the amount of content, but it'll be even more interesting content to cover. So there's still plenty of interesting stuff to learn in Haskell. I hope you're looking forward to it as much as I am.